Hello and welcome students. Today we will complete this chapter of bending stresses in the beams with the final numerical. What happens in this numerical? Let us see ahead. In this numerical, I section, unsymmetrical I section is given to you, but we have to join this I section with the mirror image of the same I section. Means when we are welding the mirror image of this I section, it will form a symmetrical I section, and we have to calculate the ratio of moment of resistance for both the sections. For which both sections? For the symmetrical sections after welding and for the unsymmetrical section which is looking over here. Let us see step by step so that you will be clear about this. Example 15.5, what is given in the data? Figure shows a rolled steel beam of unsymmetrical I section as shown in the figure. Here it is 120 and 30 dimensions for the top flange, while for the bottom flange the dimensions are 250 and 30 as shown in the figure. And here it is the width are given that 30 and 300 is the depth of the beam. If a similar I section is welded on the top of beam to form a symmetrical section, determine the ratio of moment of resistance of the new section to that of the single section. So we have to determine the moment of resistance, ratio of moment of resistance for the symmetrical sections to the unsymmetrical section. Assume the permissible bending stress in the tension and compression to be the same. So what is the solution? Given in the data is that permissible bending stress in tension is equal to permissible bending stress in compression. Actually, the value of bending stress is not given to us, so we have to consider it as a sigma only. Let us how it affects the calculation. Let us see that. First of all, let us find the center of gravity as per our usual method. Here you can see in the figure, the y-axis is always passing from the bottom. So from the bottom, you can see the y-bar is calculated. First of all, what is the y-bar? Formula of the y-bar is a1y1 plus a2y2 plus a3y3 upon a1 plus a2 plus a3. So what is a1? It is the area of part 1, which is 120 into 30. So here it is the area of part 1, 120 into 30. Now how this distance 345 becomes? It is from the bottom x-axis to the CG of the first part, which means this 30, then after 300, so total 330, plus half of 30 means 15. So it is 345. 330 plus 15, 345. Similarly for the part 2, the area will be 30 width into 300 depth. So 30 into 300 is the area of part 2. And what is the distance? It is from the center of gravity to the bottom. Means 30 plus 150, which is equal to 180. And the last area is A3, which is 250 into 30. So 250 into 30, and the distance is 15. From the center of gravity to the bottom is 15. And the last area is A1 plus A2 plus A3, which is in mm in the denominator. So final answer is 148 mm for the y-bar. So what is 148? It is the distance of center of gravity of this I section from the bottom only. So this is your y-bar. Now what is y1? It is the distance of top fiber from the calculated CG. So from this CG to the top fiber distance is known as y-bar, which is calculated by 360 minus 148 is equal to 212 mm. And y2 is our y-bar itself, which is the distance of the bottom fiber from the calculated CG, which is 148 mm. So we have calculated two most distances, y1 and y2. y1 means the distance of the given CG to the top fiber, and y2 means the distance of the given CG to the bottom fiber. Now for the calculation purpose, we will take the highest distance, which is y1, 212 mm, so that we can find the moment of resistance, maximum moment of resistance. For that we have to take the highest distance y1, which is equal to 212 mm. Now let us see how the moment of resistance will come. Let us see the moment of inertia first. Actually, what is our moment of inertia? The moment of inertia will be available by calculating the moment of inertia of separate three parts and by adding them. Okay, so here is the moment of inertia for the part number 1, here is the moment of inertia for the part number 2, and the last is part number 3. Now what is the formula for actual moment of inertia of any part? It is according to the parallel axis theorem, Ig plus AH square. Now here in this figure all the parts are rectangle, so Ig will be BD cube by 12. Area will be width into depth, and H square In that H means y1 minus y bar or y2 minus y bar or y3 minus y bar. If the answer is coming negative, then you can also take y1 minus y bar, instead y bar minus y1. So probably in the third part we will finding that the answer is negative. So in the third part we will take y bar minus y3. Let us see how. In the first part you can see here it is Ig, BD cube by 12, BD cube by 12. So what is B? According to the figure, B is 120 and D is 30. So 120 into 30 cube by 12, which will give you BD cube by 12. Area means 120 into 30, B into D. Here it is y1 minus y bar. Y bar we have calculated 148, okay, in the earlier image. So y1 is what? From the CG, from the bottom of the figure to the CG of the top part, which is equal to 330 plus 15, 345. So here it is y1 minus y bar, 345 minus 148 whole square. In the second part, here again it is BD cube by 12. B means 30, depth means 300. So 30 into 300 cube divided by 12. Area will be 30 into 300, and here it is the CG, y bar minus y2, or you can say y2 minus y bar. So y2 will be 180, means CG of this part from the bottom. 150 plus 30, 180. Minus 148 is our y bar whole square as it is. Third part. For the third part, the CG is 250 into 30. BD cube by 12 again. Area is 250 into 30. And y3 minus y bar means 148 minus 15 whole square. 148 is the CG, our y bar. And y3 means CG of this part from the bottom, which is 50. So finally you will get the answer of 350 into 10 raised to 6 mm raised to 4, this unsymmetrical section. Now what is section modulus? Section modulus Z1 is equal to I by Y. So I is 350 into 10 raised to 6, and what is Y? Y is the distance of the top fiber from the given CG, as we are taking the highest distance. So Z1 equal to 1.65 into 10 raised to 6 mm cube. Now what is moment of resistance? It is sigma into Z1. So sigma is not available to us. Z is 1.65 into 10 raised to 6, which is our answer, equation number 1. So here it is the moment of resistance for this unsymmetrical section. But what we want an welding part, means mirror image of this I section is welded together to form a symmetrical section as shown in the figure. You can see if you draw a certain line over here, the figure is symmetrical about the x-axis from both sides, top and bottom. Now let us see what happens. We have to calculate first of all moment of inertia I2. Our first moment of inertia is 350 into 10 raised to 6 for the single I section. Now we are calculating the moment of inertia for the second or entire section, this section. Then we have to multiply it by 2 times. And here it is the formula. 2 times moment of inertia plus AH square. Now what is AH square? So area is 20 into 100. You can calculate the total area of the rectangle, 20 into 100, and the distance is 212 again, means y is equal to 212, which is the distance of the CG from the top fiber from both the sides. So by keeping the same values and solving in the calculator, we will get 2506.8 into 10 raised to 6 mm raised to 4. So here is the moment of inertia for this unsymmetrical 2 becoming symmetrical Y section, symmetrical I section. Okay, this is the mirror image welded together to the original unsymmetrical section, such that the symmetrical section can be formed, and we have calculated the moment of inertia for it, which is 2506.8 into 10 raised to 6 mm raised to 4. Now what is section modulus for this section? It is Z2 is equal to Y by Y. Now how the moment of inertia is replaced over here, but how the Y becomes 360. So now the total depth you can see 30 plus 300 plus 30, which is 360, and similarly 360 in the downward image. So total will be 720. So half of this 720 will become the midpoint, which is 360. Okay, which is taken as Y. So finally Z2 will be 6.96 into 10 raised to 6 mm cube. So here it is our Z2, section modulus. Now moment of resistance is again sigma into Z2. So sigma is not available to us. Z2 equal to 6.96 10 raised to 6. This sigma is extra, printing mistake. So you just consider this. Now while we are taking the ratios, here the ratio is M2 by M1. So moment of resistance for the second part, which is welded together, and moment of resistance for the first part, which is calculated earlier. So final answer will be sigma cancelled out, and you will find the answer of 4.22. Or you can say that moment of resistance for the second sections is 4.22 times the moment of resistance for the first section if you cross multiply M1, which means what? This section, by joining two I sections, this welded section becoming more stronger, which give you more moment of resistance towards the loading. So this type of section is very strong enough to withstand the loads. Okay, so here is our fundamental for this numerical. Actually, this numerical is a very precise numerical, which is very miscellaneous type of numerical, which cannot be important for the exam point of view. It is just for the knowledge purpose of yours. So must remember that you have to calculate all the moment of inertia, all the center of gravities first of all, then after finding the section modulus and bending stresses will give you the loading condition of the given beam. Now we are concluding, or we are finishing this chapter over here, and we will meet in the next lecture with the new chapter. Our new chapter is shear stresses in the beams. So for that chapter, be ready with the revision of this bending stresses. So in the bending stresses, we have studied various numericals like bending stresses for the simple beams, bending stresses for the cantilever beams, for the symmetrical sections like rectangular, circular, hollow circular, and afterwards we have calculated the bending stresses for unsymmetrical sections also, like T sections, I sections, joint I sections, etc. Before that, we have finished some theories also, like bending equation, pure bending, assumptions made in the pure bending, then after flexure equation, which give you the equation number 1 and 2, and comparing that we are getting the triplet of the equation, which is known as flexure equation. So just rewind all this topic, revise this, ask for any doubts, and we will meet in the next lecture with the new chapter, that is shear stresses in the beam. Till then, practice yourself. Happy Thursday. Thank you, students.